So we're going to look at what are called solids of revolution, and the way these are presented is that you'll be given some kind of function, and you'll be told that that's going to be, let's just say, from A to B. Rather than consider the area, we're going to rotate that around an axis. So in this case, I'll just rotate it around the x-axis. And when you do that, you end up generating, if you imagine kind of doing that, really fast, you'll generate a solid. I tried to draw its like mirror image over here. You'll get some sort of solid. I'm also going to attach a link to a video that actually, a YouTube video that's been made that actually really gets at what's happening here if you're having a hard time visualizing. But you get a solid, and so we can actually figure out the volume of this solid. And the way we do that is you imagine slicing. Well, first of all, let's rather than kind of rotate the whole thing, in order to get a slice, let's just imagine rotating this one rectangle. Right? If you rotate that one rectangle around this axis, you can hopefully see that you get a disk. Right? And that disk, the volume of that disk is what we want to analyze. If we can get the volume of that disk, we're golden, because all we have to do is integrate, in other words, add up the volumes of all those arbitrary disks from A to B. So since it's a small change in the x direction, I call the thickness of that dx. Now the radius, hopefully you can see that the radius of this disk is actually f of x, right? So our r here is just whatever our function is, in this case at least. And therefore the volume of this little disk is pi r squared. Pi r squared times the thickness, which is dx. And so that's what we end up doing. We end up taking, and I guess my r is f of x, so I'll write that. So we end up taking one disk, analyzing it, getting its volume, and then adding up the volumes of all those disks as x goes from A to B. And that will produce the actual volume of that solid of revolution. So let's do an example now. So imagine we have a region which is described here. It's the region between the graph of f of x equals x squared, the x-axis over the interval 0 to 2, and we're revolving that around the x-axis to make a solid, and our goal is to find the volume of that solid. So like I said in other videos, I'm really just going to model the integral. I'm not going to actually do the antiderivative, because that's really not the hardest part of this. I mean, if you have a calculator or just use the fundamental theorem, you can do that. But in terms of focusing on the big idea, we'll just set up the integral. So x squared looks like this. You're going to need a pretty, a decent enough picture. We're considering the region between the x-axis and the curve on the interval 0 to 2. So this region here, we're going to be rotating that around the x-axis. So I indicate that with a little arrow like that. So our goal is to find the volume of the solid. So the way I do this is I just draw one rectangle. So this is an arbitrary rectangle. And you imagine rotating that one rectangle around. So when you do that, it creates a disk. And since the thickness here of the disk is indicated by the thickness of our rectangle, that's a small change in the x direction. We indicate that with a differential dx. The radius here, if you look back at the picture, hopefully you can see that the radius, because if I rotate my disk, sideways the disk would look like this. The radius is just the this distance right here. That's r. But that's just x squared, right? That's just f of x equals x squared. That's what that distance would be. So r equals x squared. And so therefore the volume is equal to pi r squared times dx. And that means that the total volume is equal to all of those added up as x goes from 0 to 2. And that is the answer. All right, so that one wasn't so bad. If you have a hard time visualizing it, this is almost worth, and again, like I'll attach some links to some videos, but having some manipulatives handy can actually make this, a little easier to visualize than rather than just seeing this. But if you understand why the radius is what it is, and you can analyze just this one disk, then that really is the most difficult part about it. Here we're going to look at a similar type of problem, but we're going to actually consider the same curve, y equals x squared, but we're looking at the region that's trapped between the y-axis over the y-interval 0 to 4. So that's this area here. And we're rotating that region around the y-axis. So, if we're rotating around the y-axis, in order to use the disk method, you want to draw a rectangle that's perpendicular to that axis of rotation. So I'm going to draw this rectangle here. That's the arbitrary rectangle that we're rotating. And then we analyze that. So this time, because it's a horizontal rectangle, and this is important because a lot of my students get confused by this, if you draw a horizontal rectangle, you have to be integrating with respect to y. So I got to call that thickness a small change in y, or dy. All right, and we're going to be summing those up as y goes from 0 to 4. My radius now, is this distance here, right? Because when you rotate it around, that the disk, that'll be half the diameter of the disk. So that distance there, that is an x distance. However, I need to describe it in terms of y. So let's just analyze this point right here. What would you call this point? Well, you could call it x comma x squared, because the y coordinate is x squared. But you could also call it, if you solve this for x up here, you get x equals the square root of y. So the x coordinate in terms of y is the square root of y, and the y coordinate is just y. So I'm going to use, because we're integrating with respect to y, I need to use this name here. And you need to understand that it's a x distance, so it's this x coordinate that I'm using. So r equals the square root of y. And once you've got that, you know that the volume is pi r squared dy, and therefore the total volume is just the volume of all those disks added up as y goes from 0 to 4. Right? Y is changing from 0 to 4. And that will give us the areas of all those infinitely thin disks, and therefore the volume of the entire solid.